Databases in a distributed environment. For visualization purposes, what is database first? Database refers to the data structure that stores organized information. So, database looks like this. This is Facebook's database hardwares. Why do we need database? Using database, organizations can now leverage the data they collect to run more efficiently, enable better decision-making, and become more agile and scalable. So, our report will also examine issues, features, and trade-offs in deciding and evaluating different databases. With that, companies have a discretion which database to use since databases are divided into two. Entities can have a centralized system, which is a system when all data processing is performed by large computers at a central site from the word itself, centralized system. Or a distributed data processing system in which the IT function is divided into small IT units. So, distributed databases have two more categories: partitioned database and replicated databases, which will all be discussed later. Centralized database retains the data in central location, performs the function of file manager. So, centralized databases is used by organizations such as colleges and banks. So, as we can see from figure 4.15, how centralized databases works. Remote IT units send requests for data to the central site, then the central site processes the request and transmits the data back to the remote IT units in which the actual processing is performed by them. So, the fundamental objective is to maintain data currency. Data currency in a DDP environment. So, let's define first what data currency is. Data currency is a monetary value assigned to data to identify its financial significance to an organization. To simply put, data currency is monetary value assigned to data so that it can be used as a unit of exchange in a transaction, either as a sole payment or in combination with money. So, what is happening to data currency in a DDP environment? During data processing, account balances is temporarily inconsistent because their values are incorrectly stated. For example, as seen in the PowerPoint presentation, we have a $2,000 credit sale to our customer Jones. So, the beginning balances of our AR subsidiary is $1,500 and the balance of our AR control account is $10,000. Now, we will record and add the 2,000 to the AR subsidiary having a balance of 3,500. But, as we add the 2,000 to the subsidiary or the instruction number 3 before the instruction number 4, we can clearly see that the AR control account is temporarily inconsistent for the value of $2,000. Only after the transaction number 4 will the inconsistency is resolved and the 2,000 is recorded. What happened is that there is a corruption of data.
Let's take a look at a slightly more complicated example. Let us consider the processing of two separate transactions from two remote IT units. Transaction 1, which is the sale of 2,000 on accounts to customer Jones from IT Unit A, and Transaction 2, which is the sale of 1,000 on accounts to customer Smith from IT Unit B. We can see in the table that Jones has 1,500 in his accounts receivable subsidiary account, and Smith has 3,000 as their beginning balances. In the AR control account, Jones has 1,000. And to record the transaction of 2,000 sales on account to Jones, 2,000 is added to his AR subsidiary account, totaling 3,500. Notice that IT Unit B hold the AR control data at 10,000 when it was in an inconsistent state. Therefore, instead of 13,000, the new AR control balance is misstated at 11,000. How to solve this misstatement? The solution to this problem is to employ a database lockout. Database lockout is a software control that prevents multiple simultaneous accesses to data. So, to apply database lockout to the illustration we are discussing, upon receiving the access request from IT Unit A, for AR control number 2, the central site should place a lock on the AR control to prevent access from other units until transaction 1 is completed. Then, when IT Unit B requests AR control, it is placed on wait status until the lock is removed. When Site A's transaction has been posted, IT Unit B is granted access to AR control and can then complete transaction number 2. That is how to solve the misstatement.
Next is distributed databases. From its word, distributed. Distributed databases can be either partitioned or replicated. Join us as we dig deeper on the concept of distributed databases. Partition databases. A partition database approach splits the central database into segments or partitions that are distributed to their primary users. Now, let's unfold the advantages of partition databases. First, having data stored at local sites increases users' control. Next, transaction processing response time is improved by permitting local access to data and reducing the volume of data that must be transmitted between IT units. Third, partition databases can reduce the potential effects of disaster by locating data at several sites. The loss of single IT unit does not eliminate all data processing by the organization.
As you can see in the figure 4.16, primary users of data A and B request data to primary users data C and D.
And data C and D request for data to the primary users of data E and F, and vice versa. Moreover, Figure 4.16 works best for organizations that require minimal data sharing among their distributed IT units. The primary users manages data requests from other sites.
To minimize data access from remote users, the organization needs to carefully select the host location. Identifying the optimum host requires an in-depth analysis of user data needs. The deadlock phenomenon. In a distributed environment, it is possible for multiple sites to lock out each other from the database, thus preventing each other from processing its transactions. It is a situation when two processes sharing the same resource are effectively preventing each other from accessing the resources. As you can see in the figure 4.17, it illustrates three IT units and their mutual data needs. Notice that Site 1 has requested and locked data A and is waiting for the removal of the lock on data C to complete its transaction.
Site 2 has a lock on C and is waiting for E. Finally, Site 3 has a lock on E and is waiting for A.
A deadlock occurs here because there is mutual exclusion to the data resource and the transactions are in a wait state until the locks are removed. This can result in transactions being incompletely processed and the database being corrupted. For example, imagine that there is only one side of the road and two vehicles meet in the middle. What they have to do is one has to let go for the other to continue moving forward. It is because it is a one-sided road and there is no space for the both of them. And if both of them are not ready to let go, then that situation is a deadlock. Deadlock is a permanent condition that must be resolved by a special software that analyzes each deadlock condition to determine the best solution. Because of the implication for transaction processing, accountants should be aware of the issues pertaining to deadlock resolution. So what are the conditions to be met for the deadlock? Firstly is mutual exclusion, meaning it is not shareable and only one process can use it at a time. Second, hold and wait, which is holding one resource and waiting for another resource to come. Third is no preemption. A resource can be released voluntarily by the process itself. And lastly is the circular wait. In other words, it is called dead end. Now we're going to deadlock resolution. Resolving a deadlock usually involves terminating one or more transactions to complete processing of the other transactions in the deadlock. The preempted transactions must then be reinitiated. In preempting transactions, the deadlock resolution software attempts to minimize the total cost of breaking the deadlock.
These are the factors that need to be considered in this decision. The first one is the resources currently invested in the transaction. This may be measured by the number of updates that the transaction has already performed and that must be repeated if the transaction is terminated.
The transaction stage of completion. In general, deadlock resolution software will avoid terminating transactions that are close to completion.
And lastly, the number of deadlocks associated in the transaction. Because terminating the transaction breaks all deadlocks involvement, the software should attempt to terminate transactions that are part of more than one deadlock.
Now, let's move on to replicated database. What is replicated database? It is a database where data is stored in more than one site or node. Basically, it is useful for improving the availability of data on companies wherein there is a high degree of data sharing but no primary user. It is simply copying data from a database from one server to another so that all the users can share the same data. In figure 4.18, we can see that the database was replicated at each site. Data A, B, C, D, E, and F were made available for Site 1, Site 2, and Site 3. Data traffic between sites is reduced considerably since common data are replicated at each IT unit site. Thus, the pros of replicated database include load reduction. Due to the reason that replicated data can be spread over several sites or servers, it eliminates the likelihood that any server will be overwhelmed with user queries for data. Next is the efficiency. Servers of sites that are less burdened with queries can offer improved performance to fewer users. And lastly, high availability. Utilizing multiple servers with the same data guarantees high availability, meaning that if one server goes down, the entire system can still provide acceptable performance.
Let us now proceed to the disadvantages of replicated database. The problem with this approach is maintaining current versions of the database at each site. As each IT unit processes only its transactions, common data that were replicated on each site are affected by various transactions and reflect different values. Evidently, figure 4.19 demonstrates the effect of processing credit say for Jones at site A and Smith for site B. We can see the starting balance of AR control was $10,000. After the transactions are processed, we can see that the value shown for the common AR control account was inconsistent and incorrect at both sites. IT Unit A reflects $12,000 while IT Unit B reflects $11,000. Therefore, the cons of replicated database include number 1, data inconsistency. Similarly, incorrect or out-of-date replicas can cause different sources to be out of sync with each other. This may lead to wasted data warehouse costs that are spent needlessly analyzing and storing irrelevant data. Number 2, data loss. Data loss can occur during replication when incorrect data or updates of a database are copied and consequently, important data is deleted or unaccounted for. This can happen if the primary key used to verify the quality of data in the replica is malfunctioning or incorrect. And number 3, multiple servers. Running multiple servers has an inherent maintenance and energy cost associated. It requires either the organization or a third party to address this cost. If a third party handles them, the organization runs the risk of vendor lock-in or service issues beyond the organization's control.
Let us now proceed with concurrency control. It ensures that correct results for concurrent operations are generated while getting those results as quickly as possible. Database concurrency is the presence of complete and accurate data at all user sites. The commonly used method for concurrency control is to serialize transactions. Serialization is the process of converting an object into a stream of bytes to store the object to a memory, a database, or a file. A transaction is serializable if it is equivalent to a serial schedule. The method of serialized transactions involves labeling each transaction by 2 criteria. First, special software groups transactions into classes to identify potential conflicts. For example, read-only or query transactions do not conflict with other classes of transactions.
The second part of the control process is to use timestamps on each transaction. Here, the organization uses a system-wide clock to keep all sites on the same logical time. If conflicts exist, transactions are entered into a serialization schedule which permits transactions in the schedule to be processed by the IT units in a predefined order. Next is the database distribution methods and the accountants. Many issues and trade-offs has to be considered in deciding on what database distribution methods to be applied. Decisions on whether to use centralized or distributed database or what approach would be most desirable could impact the organization's ability to maintain data integrity. Thus, the auditor's key concern here would be the preservation of audit trails and the accuracy of accounting records that could impact their engagement.